This is a very important result as you see, you can obtain the joint distribution of random vector y through the joint distribution of x in a quite easy way. Uh, you just compute the inverse of your transformation matrix, and you have the random vector which has the components of the new transformed random variable. And if you divide that by the absolute value of the determinant of A, you get the distribution. It's that easy. And also, as I said, it's generalizable to higher dimensions. And if if the transformation matrix A is not invertible, you have to treat some of the components separately. Just make um, uh, matrix A invertible by removing some of the components of Y. Um, or in some cases, of course, matrix A may not be square. For instance, take the very simple case of y equals x1 plus x2, right? When you have such a transformation, obviously your transformation matrix is not a square matrix because this is just 1, 1 times x. This is your transformation matrix, which is clearly not square. What you do here is you can introduce auxiliary variables. You can just define this to be y1 and define y2 as, let's say, x2, okay? And then you can write y1, y2 equal to 1, 1, 0, 1, x1, x2, okay? And now you have a square matrix, which is in fact invertible. And then you can compute the joint distribution of y1, y2 through this. And if you need the marginal distribution of y1, you just integrate it with respect to y2 and then obtain the marginal distribution of y1. That's what you can do. If you have it the other way around, if you have more y random variables than x's, for instance, let's say y1 equals x1 plus x2, y2 equals x1 minus x2, and y3 equals 2x1 plus 3x2. Okay, so in this case, obviously, y1, y2, y3 equals 1, 1, x1, x2, and then for y2 you have 1 and minus 1, and for y3 you have 2, 3, right? Now, what to do with such a matrix? And here we did this by defining an auxiliary y random variable. And here you see A matrix is rectangular, but tilted to the other side. We have more y's than x. So here you'll just define auxiliary x. You can write x1, x2, x3, and a column of zeros here. But that will give you a matrix which is still not invertible. So what you can do is separate these. For instance, you can obtain the joint distribution of y1 and y2 by defining a transformation with this matrix, okay? Or maybe you can write the joint distribution of y2 and y3, and so on. So in each case, you need to do a manipulation of your original distribution or original definition of transformation so that you can apply this formulation. And at this point, I will also give you the expression for general transformations, which I will not really derive. For the derivation, you can actually look at the textbooks, which is not that difficult, but you'll have to use some results from multivariable calculus, and I'm not going to go into that. Um, and here the definition is we have random vector x and random vector y, And random vector y is defined as a function of random vector x as seen here, okay? And if you assume the g functions are invertible, and we will write the inverse of each g function is denoted by these h functions. And remember, the functions g here need not be linear functions, okay? They might be any function which is essentially invertible. And in this case, the joint density of y can be written as this expression in terms of the joint density of x applied to these points. And here you have again a determinant, and this is called the Jacobian of the transformation. Okay, so you have partial derivatives, the derivative of g1 with respect to x1, x2, x3, etc. in the first row. In the second row, you have the derivative of g2 with respect to x1, x2, x3, etc., and so on. Okay. Again, as I said, if the dimensions of x and y are different, you can define auxiliary variables or functions in this case to obtain the joint distribution of y. This is in general how you obtain the density of a transformed random vector. But in the general sense, we will in this course deal with linear transformations only.